the really difficult ones are at the start of this tutorial. I know it's a little bit off-putting, but I think we just need to really tackle them from the beginning, really difficult ones, and see how we get on. Okay, question 1. Hydrogen atoms in an ultraviolet lamp make transitions from the first excited state to the ground state. So let's just analyse that sentence for a second. We've got the first excited state, got the ground state, that's n equals 1. This is n equals 2. And we saw this in the previous topic. And we know that when an electron makes a transition from there to there, it emits a photon. And we know this is a hydrogen atom. And you'll remember from Bohr's model, we know that the energy of each electron state is minus 13.6 electron volts divided by n squared. Right, we've analysed that first sentence. Let's go on to the next sentence. Photons are emitted and are instant on a photoelectric surface as shown. So we've got the energy levels here inside this lamp, and then we're looking at the photoelectric effect here. A. Show that the energy of photons from the UV lamp is about 10 electron volts. So we want to analyse this concept we've just talked about, the concept of the electron jumping down from the first state to the ground state and releasing a photon. This is n equals 2, this is n equals 1. From the first state, the energy of the first state will be minus 13.6 electron volts divided by 2 squared, which gives us 3.4 electron volts. So here we got minus 3.4 electron volts. And for the ground state, we've got minus 13.6 divided by 1, which gives us 13.6. You'll notice I haven't included the negatives here just because it doesn't really matter at this stage. The negative just shows that it's bound to the nucleus and that the energy of the electron after it's free is equal to 0 in comparison. So the energy lost in that transition is our change in energy, which is 13.6 minus 3.4, which gives us 10.2 electron volts. And the question says prove that it's about 10 electron volts, which is around 10. The photons cause the emission of electrons from the photoelectric surface. The work function of the photoelectric surface is 5.1 electron volts. So we're now looking at the photoelectric effect, and we know the work function is 5.1. We know that the electron that's being released has energy of 10.2 electron volts. Calculate in joules the maximum kinetic energy of the emitted electron. I just want to draw a diagram here. Okay, we're going to have an incoming UV photon, and that's got energy of 10.2 electron volts. 5.1 electron volts is used to release that electron from this photoelectric surface, and then any energy left is released as kinetic energy. And that takes us to the photoelectric effect equation. HF equals the work function plus kinetic energy. We want to find out what kinetic energy is, so EK equals HF minus that. HF is the energy of the photon, so equals 10.2 electron volts minus 5.1 electron volts, which gives us a value of 5.1 electron volts. We know the kinetic energy is 5.1 electron volts, but it does ask us to calculate it in joules. So we do 5.1 times 1 electron volt, which is 1.6 times 10 to the minus 19, which gives us a value of 8.2 times 10 to the minus 19 joules. And that will be given to two significant figures, so that's absolutely fine. B2. Suggest, with reference to the conservation of energy, how the variable voltage source can be used to stop all emitted electrons from reaching the collecting plate. Now we're going to a completely different part of this experiment. Let's go back to the diagram. We've looked at the energy levels and the UV photons being released from the UV lamp. We've looked at the photoelectric surface and that being the photoelectric effect. What we're now going to look at is this section here. Once the electrons have been emitted, what happens when we put a variable voltage source across it? So I'm going to redraw it here. So we've got the photoelectric surface, we've got little electrons being emitted with kinetic energy. They have kinetic energy, and they're travelling towards another plate. There is a voltage source across that plate, and it can be varied. Okay, it can be any value. The first thing we'll want to talk about in terms of energy is the kinetic energy of the electrons. So what we'll say is the electrons are emitted from the photoelectric surface with kinetic energy. The second thing we'll want to know is that the variable voltage source, or the battery, will do work on these electrons and transfer electric potential energy. And finally, I think we should finish this description off by saying when the electric potential energy is equal to the kinetic energy, the electrons will stop. And I think that's a pretty good explanation of why the electrons will stop in terms of the conservation of energy. The electric potential of the photoelectric surface is 0 volts. The variable voltage is adjusted so that the collecting plate is at negative 1.2 volts. C1. On the diagram, draw and label the equipotential lines at minus 0.4 volts and minus 0.8 volts. So what we've got here is minus 1.2 volts. Got 0 here, and we'll have electric field lines, uniform electric field lines, heading down like this. They are straight, they're equally spaced, and we won't bother with the edge effect right now. But the question doesn't ask for the electric field lines, it asks for the equipotential lines. And you'll remember that the equipotential lines are at right angles to the field lines. So we want to draw two lines at right angles to the field lines. 0.4 and 0.8 each represent 1/3 and 2/3 of 1.2. So we want to draw our equipotential lines 1/3 of the way across for 0.4 and 2/3 of the way across for 0.8 volts. And we want to make sure they're at right angles to the field lines. C2. An electron is emitted from the photoelectric surface with kinetic energy of 2.1 electron volts. Calculate the speed of the electron at the collecting plate. Right, let's draw this again. We've got an electron being emitted here with 2.1 electron volts. However, across these plates is a battery which provides 1.2 electron volts. That means that the kinetic energy of the electron is going to decrease by 2.1 eV minus 1.2 eV minus. It's going to have 0.9 electron volts when it reaches this collecting plate here. And we're going to use that to calculate the speed of the electron. EK equals a half mv squared. We need to change our value for kinetic energy into joules. So 0.9 times 1.44 times 10 to the minus 19 joules. And we want to rearrange for V. So V equals the square root of 2ek over m. Pop in all our values. 2 times 1.44 times 10 to the minus 19. This is the mass of an electron, which you can get from your data booklet. And if we pop all the values in, we'll get 5.6 times 10 to the 5 metres per second. Is that a reasonable value? Well, yes, it is a reasonable value because we know it can't go faster than the speed of light or really within 10% of the speed of light. So that makes quite a good value for the speed of the electron. I'm happy with that. Question 2. Which of the following is evidence for the wave nature of the electron? When we're thinking about the wave nature of electron, we're trying to prove that a particle has wave-like properties. And you'll remember, it's similar to the experiment we looked at before. We take an electron, we accelerate it through an electric field. And once we've accelerated it to a speed, we put it through a very small and thin graphite structure. And what we see is that these electrons are diffracted. And that diffraction of the electron proves to us that the electron has a wave nature and wave-like particles, and that is evidence for the wave nature of the electron. So we want to see the word diffraction. Diffraction, I'm instantly going to go with this, but let's just check. Is the continuous energy spectrum in beta minus decay proof of this? No. Is the existence of atomic energy levels proof of the wave nature of electron? No. Is the existence of nuclear energy levels? No. We know it's electron diffraction. Just remember that electron diffraction is proof for the wave nature of the electron. Question 3. A photoelectric cell is connected in series with a battery of EMF 2 volts. Photons of energy 6 electron volts are instant on the cathode of the photoelectric cell. The work function of the surface of this cathode is 3 electron volts. What is the maximum kinetic energy of the photoelectrons that reach the anode? Let's think about this logically. HF equals the work function plus kinetic energy. And we want to find out what the kinetic energy is. EK equals HF minus the work function. HF is the energy of the photon, the instant photon, so that's 6 electron volts, minus the work function, which is 3 electron volts. So your answer might be that the kinetic energy is 3 electron volts. However, this photoelectron is leaving with a kinetic energy of 3 electron volts. But there's work being done by the anode that opposes the kinetic energy on the photoelectron. And the work being done is 2 volts. Work done is equal to QV, and the charge on an electron is E. So EV, which is E times V, which is voltage. So it's 2EV. So actually what's happening is that kinetic energy of 3 electron volts, 2 electron volts of work is being done on it by electric potential energy. So it's only left with EK equals 1 electron volt. The answer is A. Question 4. When green light is instant on a clean zinc plate, no photoelectrons are emitted. What change may cause the emission of photoelectrons? So we've got a zinc plate, and that zinc has a work function that doesn't change. So the work function for zinc is immovable. We have a green light photon that's instant on it. What we can change to increase the energy of that is we can increase the frequency. So we could have a blue light or ultraviolet. That would increase the frequency of the photon, which would increase the energy to overcome this work function. Let's see if that's the answer. What change might cause the emission of a photoelectron? A. Using a metal plate with a larger work function. Well, that's not going to work, because if the work function is larger than zinc, then it's going to be harder for that green light to overcome the work function. So it's not A. B. Changing the angle of incidence of the green light on the zinc plate. That makes no difference. C. Using a shorter wavelength. Well, a shorter wavelength means a higher frequency, which means a higher energy of photon. So yes, that works. D. Increasing the intensity of green light. That doesn't work. If it was a wave, if we were looking at light as a wave, then increasing the intensity would be increasing the amplitude by a factor of squared, and then the energy, yes, would increase significantly. But light isn't a wave in this case. We're looking at light as a particle, and it doesn't work. So the answer here is C. The next 2 questions are trick questions, I think. I always get caught out by them, but you're not going to. And I'm going to explain to you exactly where these tricks lie, so you can spot them when it comes to an exam. Question 5. Photons of a certain frequency instant on a metal surface cause the emission of electrons from the surface. So we've got the surface, it's got a work function like this, photon instant on it, HF, and it causes the electron to be emitted. The intensity of the light is constant. Okay, so intensity is constant. What is intensity? A lot of students think that the intensity is the number of photons. Instead, the intensity is the energy per unit area per unit time. And we need to bear that in mind as we go through this question. The intensity is the energy per unit area per unit time. So the intensity stays constant and the frequency of the photons is increased. So we've got the frequency of the photons increased. That means that the energy of the photon increases, which means that the kinetic energy of these photoelectrons increases as well. What is the effect, if any, on the number of emitted electrons and the energy of the emitted electrons? Well, we know that the energy of the emitted electron is going to increase. So we want to tick that and that. The intensity of the light is constant, but that doesn't mean that the number of photons is constant. It means that the energy per unit area per unit time is constant. So that actually means that the number of emitted electrons decreases. So the answer is B. We're going to take this concept and apply it to the next question as well. Question 6. A metallic surface is first irradiated with infrared radiation and photoelectrons are emitted from the surface. So we've got photoelectrons emitted with kinetic energy. We've got infrared radiation. The infrared radiation is replaced by ultraviolet radiation of the same intensity. So we've got same intensity, but that does not mean that the number of photons is the same. What it means is that the energy per unit area, per unit time is the same. But the frequency is increased because it's ultraviolet radiation. Let's just go to the kinetic energy of the photoelectrons first. That's going to increase, so it's going to be A or C. The rate of photoelectrons ejected is actually going to decrease because the intensity or the energy per unit area per unit time stays the same, but the frequency has increased. So our answer is A. Luckily, this concept is really only ever assessed in paper 1, and it's just a little quirk of paper 1 examiners that you need to make sure you understand. But the good news is if you don't get it right now and you forget all this, then it's just 1 mark you've lost. But the even better news is now you know this little quirk, you actually will never lose this 1 mark. You'll always get it. Question 7. Monochromatic light of very low intensity is instant on a metal surface. The light causes the emission of electrons almost instantaneously. Explain how this observation does not support the wave nature of light. Let's just draw a little diagram because we want to do an explain question. We've got our photoelectric surface, the work function. We've got low intensity light instant on that photoelectric surface, and the electron is instantaneously emitted. For our keywords, we want to use intensity. We want to use energy. We want to use something to do with instantaneous or time. I think we probably want to use amplitude. And the phrase we want to use is intensity is energy per unit time per unit area. That's one phrase we want to use. We want to use intensity is amplitude squared, and we'll want to say something like waves would add energy with time. So what we want to say is low intensity light has low energy per unit time per unit area. Then we want to point out that if light were a wave, the wave would eventually transfer enough energy to the electron to emit it. And finally, we want to say, given that the process is instantaneous, means that light is not a wave. Let's go back to our diagram. Let's go back to our quadrant and see if we've got everything we need here. Have we included the word intensity, energy? Yep. Have we included instantaneous time? Yep. We haven't included amplitude, and I don't think actually we needed to put that in here. But we have included this idea and this idea. I'm really happy with that answer. The second part of this question asks to explain why photoelectric effect with low intensity light does support the photon nature of light. We'll go back to our quadrant. And I'm going to draw this diagram again because it's going to help us a bit more this time. Electron with kinetic energy. This time we definitely want to use the word photon. We want to use interact. We want to use instantaneous. And we want to use transfer of energy. We also want to say one photon transfers energy to one electron. And we want to say the transfer is instantaneous. And the first part of this explanation will say that a photon of light is a packet of energy. Secondly, it will say each photon interacts with one electron and transfers its energy instantaneously. And finally, it will say this allows the electron to leave the metal immediately. Let's just go back and check that we've got everything we need. I think the diagram is accurately described. We've used the words photon, we've used interact, we've used instantaneous, we've used transfer of energy, and yeah, we've used everything. I'm happy with that. In an experiment to demonstrate the photoelectric effect, light of wavelength 480 nanometers is instant on a metal surface. The graph shows the variation of the current I in the ammeter with the potential difference V of the cathode. And what this graph shows is when there's a current, it means, I'm going to go back up to the diagram, that there's electrons leaving and moving across to the cathode. So here, when there's no voltage across the cathode and the anode, then there's a current flowing of electrons. When they left that surface, had kinetic energy of 1.5 electron volts. How do we know that? Because it required us to do work on those electrons of EV, or QV, but then it's EV because it's electron volts, of 1.5 electron volts to counteract the kinetic energy that they had. Calculate in electron volts the work function of the metal surface. So we know that the photon instant on the metal surface is HF, but we were only given wavelength, so HC over lambda. We can work that out. 4.143 times 10 to the minus 19 joules, but we want that in electron volts. So we divide it by 1.6 times 10 to the minus 19, which gives us a value of 2.59 electron volts. That's how much energy each photon has as it comes in to the photoelectric surface. 2.59 electron volts. The work function we want to find out, and we know that each electron leaves with an energy of 1.5 electron volts. So, HF equals the work function plus kinetic energy. The work function equals HF minus the kinetic energy, and HF, of course, is just the energy of the instant photon. So it's 2.59 electron volts minus 1.5 electron volts gives us a value of 1.09 electron volts, but let's put it to two significant figures, 1.1 electron volts. B2. The intensity of light instant on the surface is reduced by half without changing the wavelength. So the energy of the photons stays the same because the wavelength stays the same, but the intensity has decreased. Draw on the graph the variation of the current I with potential V after this change. By decreasing the intensity and keeping the energy of the photons the same, it means there's going to be less photoelectrons emitted. But they'll still have the same energy. If there's less photoelectrons emitted, that means the current will be less. That relates to that. But if they still have the same kinetic energy, it still means that there'll be no current at minus 1.5 volts. And that links to that. So we have to represent that on the graph. Let's go back to the graph. We still want to make sure there's zero current here at 1.5, but given that there's less electrons emitted, less photoelectrons emitted, that means there's less current when there's no voltage across it. We want to represent that on this point here. So it has the same curve, but just going up to a slightly different value. Question 8. 3 observations of the behaviour of electrons are: electron emission as a result of the photoelectric effect. Yeah, electrons do that. Electron diffraction as an electron interacts with an atom. Yeah, electrons do that. Emission of radio waves as a result of electrons oscillating in a conductor. Yeah, electrons do that. Oh, here's the question. Which observations are evidence that electron behaves as a particle? Right. Well, electron diffraction is electron behaving as a wave, so it's not that. Electron emission as a result of photoelectric effect, that looks like a particle. You can actually have envisioned the particle being released from the photoelectric surface. An emission of radio waves as a result of electrons oscillating in a conductor. Well, electrons oscillating sounds like something a particle would do, so I think 3 is good. So I'm going to go with 1 and 3. B. Question 9. A beam of monochromatic radiation is made up of photons, each of momentum p. So we've got lots of little photons, each of momentum p. And they got energy E equals hf. E equals hf. E equals hf. They all got the same energy and the same momentum. Great. The intensity of the beam is doubled without changing the frequency. Okay, so they've doubled it by adding more photons. What is the momentum of each photon after the change? Well, each photon hasn't changed at all. The photon is exactly the same. It's still got momentum p. It's still got the same frequency. It's still got the same energy. So the momentum of the photon is the same. The answer is B. Question 10. The de Broglie wavelength of a particle accelerated close to the speed of light is approximately this. So this is our wavelength of a particle that's moving really fast. A beam of electrons of energy 4.2 times 10 to the electron volts is produced in an accelerator. So we've got electrons moving very fast, and they've got kinetic energy of 4.2 times 10 to the 8 electron volts. Show that the wavelength of an electron in the beam is about this. Okay, that's easy enough. Just use the equation above. The only fancy thing I've done in here is change the electron volts into joules. And that's going to give us an answer of 2.96 times 10 to the minus 15 metres. And that is, of course, 3 times 10 to the minus 15 metres, or 3 femtometers. The electron beam is used to study the nuclear radius of carbon-12. The beam is directed from the left at a thin sample of carbon-12. A detector is placed at an angle theta relative to the direction of the incident beam. The graph shows the variation of intensity of the electrons with theta. There is a minimum intensity for theta equals theta naught. Now, whenever I see this graph, I write down this equation. I write down sine theta equals lambda over d. That is the equation we use in terms of the diffraction of electrons as it goes past a nucleus. This is the nuclear diameter. This is the wavelength of the electron. And remember, that's a de Broglie wavelength, which is lambda equals h over p, h over mb. And theta is this angle here. This is not given in the data booklet for this topic, so it's really worth you memorising that whenever you see this graph. B1. Discuss how the results of the experiment provide evidence for matter waves. Before we answer this question, let's go back to the diagram setup. I'm going to draw a diagram here that looks like a screen, okay? And if you think about before, when we were looking at waves going through a small slit and then they became diffracted. And when on the screen, what you'd see is you'd see an intensity pattern. You'd see a maximum, another maximum, another maximum, 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 and in between you'd see the minimums. And in fact, the intensity pattern looked like this. If you remember, that's from the waves topic. Okay? So if you diffract a wave through a small slit or around an obstacle, you get an intensity pattern on the screen that looks like that. Now, the same thing was noticed for electrons. We've got an intensity pattern. We've got a high intensity here, and then a lower intensity and a lower intensity and so on. And that's what the detector's picking up, right? And if you get an intensity pattern from diffraction, it means there must be waves there. It's wave-like properties. That's what's happening, right? That's what this graph is. This graph is showing that the intensity of electrons varies with a wave-like diffraction pattern. The kicker here is, even if you send one electron through at that speed, you'll still see that pattern. That means that it's not just loads of electrons hitting the screen and causing this intensity pattern. If you put one electron through here, it has the wave-like properties to cause this intensity pattern. Now back to the question. Discuss how the results of the experiment provide evidence for matter waves. The intensity pattern produced by the detector shows that of a diffraction pattern. The second point we'll make is the same intensity pattern was produced even when one electron was fired through carbon-12. The final point we'll make is that diffraction patterns are a wave-like property meaning the electron must be a wave. And I'm going to put in a little caveat here at high speeds, because we know that when it goes much slower, that changes the wavelength of the electron. B2. The accepted value of the diameter of carbon-12 nucleus is 4.94 times 10 to the minus 15 metres. Estimate the angle theta naught at which the minimum intensity is formed. So we're going to use that formula. Sine theta equals lambda over d. We know what d is, and we want to know what this is. And actually in the previous question, we found out that the wavelength of the electron is 2.96 times 10 to the minus 15. So this should be pretty simple. Sine theta naught equals 2.96 times 10 to the minus 15 divided by 4.94 times 10 to the minus 15, which gives us an answer of 0.599. So theta naught equals the inverse of sine 0.599. Make sure your calculator's on the right mode here. Mine is in degrees, so it's going to give me theta naught equals 37 degrees. If your calculator was in radians, it would give you a different value. B3. Outline why electrons with energy of approximately 10 to the 7 electron volts would be unsuitable for the investigation of nuclear radii. The original energy, E1 let's call it, was 4.2 times 10 to the 8 electron volts. And that gave us a wavelength of the electron of 2.96 times 10 to the minus 15 metres. If we look at the energy up here, that's going to be a smaller energy. So E2 is smaller, which means the frequency is smaller, which means the wavelength is greater. So we're going to get a wavelength that is greater than 2.96 times 10 to the minus 15 metres. Let's say the wavelength is around about, just making a guess, I'm just making a guess, let's say it's 3 times 10 to the 14, minus 14 metres. Your nucleus has a diameter of 10 to the minus 15 metres. And when you've got a wavelength that's the same size or magnitude as the diameter, then it's going to refract loads. That's just a law of diffraction. If your wavelength is much larger, 10 to the minus 14 is much larger than the size of the nucleus, diffraction is less. And that really screws up the experiment, because you won't then get your graph that looks like this for the intensity, and you can't really do much stuff with it. So the reason why electrons with energy of approximately 10 to 7 electron volts would be unsuitable for the investigation of nuclear radii is, 1, because the wavelength of the electron is much larger. This means the wavelength is greater than the nucleus and a diffraction pattern is not observed. C. Experiments with many nuclides suggest that the radius of a nucleus is proportional to a to the power of a third, where a is the number of nucleons in the nucleus. Show that the density of a nucleus remains approximately the same for all nuclei. This was actually proved in E2. Let's go with this. Density equals mass over volume. Let's look at mass first. As you increase the number of nucleons, you can imagine that the mass will increase proportionally, right? It just makes sense. If you add more nucleons, the mass gets bigger at the same rate. So mass is proportional to the nucleon number. So we can actually say mass equals K1A, and K1 is just a constant. Let's look at volume. Assume the nucleus is a sphere, and the volume of a sphere is 4 over 3 pi r cubed. We're told in the question, we also know that r is equal to r naught a to the power of a third. So V is equal to 4 over 3 pi r naught a to the power of a third cubed. That brings us out to 4 over 3 pi r naught cubed a, and this is all a constant. So that tells us that V is equal to constant K2 times A. Great. So we've got M equals K1A, V equals K2A. So the density is equal to K1A over K2A. These A's cancelled. The density is equal to K1 over K2, which is a constant. It's the same for all nuclei. Question 11, and it's another one of these slightly tricky ones about the photoelectric effect. Monochromatic light is instant on a metal surface and electrons are released. The intensity of the instant light is increased. So intensity is increased. But, wait a minute, the frequency stays the same. So, in this case, the number of photons must increase to keep the intensity bigger, which means the number of emitted electrons will increase. Okay, let's go to the question. What changes, if any, occur to the rate of emission of electrons and to the kinetic energy of the emitted electrons? Well, so given that the frequency of the photon is the same, then there's no change to the kinetic energy of the emitted electrons. However, the intensity is increased without the frequency changing, which means the number of photons instant must increase, which means the number of emitted electrons increases. The answer is D. Question 12. In an experiment to demonstrate the photoelectric effect, monochromatic electromagnetic radiation from source A is instant on the surfaces of metal P and metal Q. Observations of the emission of electrons from P and Q are made. The experiment is then repeated with two other sources of electromagnetic radiation, B and C. The table gives the results for the experiment and the wavelengths of the radiation sources. Radiation source A has the smallest wavelengths, so it's got the highest frequency. And radiation source C has got the lowest frequency because it's got the longest wavelength. That means that the energy of the A photons is greatest and the energy of the C photons is least. And then there's electrons emitted, blah, blah, blah. We'll work out what that all means as we go through the question. A1. Outline the cause of the electron emission for radiation A. So for radiation A, there is electrons emitted in both metal P and Q. That means that radiation A, the photons have enough energy to release the electron from the work function and then give it kinetic energy. But what it says in this question is, outline the cause of the electron emission for radiation A. It's the photoelectric effect. And what that means is the energy of the instant photon is transferred to the electron. And I think we should finish it off by saying some energy is used as the work function to release the electron, and the rest of the energy is given the electron kinetic energy. I feel like I've definitely written too much there, but, why not? E.2. Outline why electrons are never emitted for radiation C. We noticed that earlier, didn't we? The wavelength for radiation C is long, meaning the frequency and energy is low. And we'll finish that off by saying the energy of the photon is not enough to overcome the work function. And I'm going to put a little bit on the end here and release the electron. I know I'm probably writing too much here, but I don't really mind. I want to get my proper explanation across. A3. Outline why radiation B gives different results. Let's go to radiation B. With radiation B, we've got a kind of average wavelength. Some electrons are emitted from metal P and no electrons are emitted from metal Q. That means that the work function for metal Q is greater than the work function for metal P. The work function, I'll just write that down, the work function for metal Q is greater than the work function for metal P. Now part B, explain why there is no effect on the table of results when the intensity of source B is doubled. Well, by increasing the intensity, we don't increase the energy of the photon. The photon still does not have enough energy to overcome the work function. C. Photons with energy 1.1 times 10 to the minus 18 joules are instant on a third metal surface. Let's draw that. The maximum energy of electrons emitted from the surface is 5.1 times 10 to the minus 19 joules. Calculate in EV the work function of the metal. So we've got the energy of the photon equals the work function plus the kinetic energy of the electron. We know that this is 1.1 times 10 to the minus 18. We want to work out what that is. And we know that this is 5.1 times 10 to the minus 19. So the work function is equal to, which gives us a value in joules of 5.9 times 10 to the minus 19 joules. But of course we want that in electron volts, so we're going to divide by 1.6 times 10 to the minus 19. And that gives us a work function of 3.6875 electron volts, which we will give to two significant figures. Question 13. In an electric circuit used to investigate the photoelectric effect, the voltage is varied until the reading in the ammeter is 0. The stopping voltage that produces this reading is 1.4 volts. That tells us the electric potential energy required to stop these kinetic energy of the electrons is equal to 1.4 electron volts. So that means that the kinetic energy of the electrons as they're released from this photoelectric surface is 1.4 electron volts. We'll take that forward. A. Describe the photoelectric effect. Let's start by mentioning photons. Photons of energy E equals HF are incident on a metal surface. Each photon interacts with an electron and helps it escape the metal surface. And finally, we'll put each photon must be above a certain frequency to overcome the work function of the metal. Again, I think I've probably given a little bit too much there, but it works for me. B. Show that the maximum velocity of the photoelectrons is, as we discussed above, the kinetic energy of the photoelectrons is 1.4 electron volts. So half mv squared equals 1.4 times an electron volt, which is 1.6 times 10 to the minus 19 joules. So V equals the square root of 2 times 1.4 times... Just rearranging this equation now for M. M is the mass of the electron. Popped all of that into my calculator and I've got 7.01 times 10 to the 5 meters per second. And does that seem reasonable? Well, yes, because we want it in kilometers per second. So if we did that, we'd be like 700 times 10 to the 3, which is meters per second. But that is also 700 kilometers per second. So that works. Just a note here, I've been writing meters per second like that. You know the notation is supposed to be like that. I mean, they're both the same, but I think fancy physicists prefer that. So if you've got kilometers per second, you'd write that. C. The photoelectrons are emitted from a sodium surface. Sodium has a work function of 2.3 electron volts. Calculate the wavelength of radiation incident on the sodium. State an appropriate unit for your answer. We know that the kinetic energy of the electron was 1.4 electron volts. So the energy of the incoming photon has to be 2.3 electron volts plus 1.4 electron volts, which gives us 3.7 electron volts. We need to put that into joules. And that tells us that the energy of the incident photon is 5.92 times 10 to the minus 19 joules. Now, E equals HF, which equals HC over lambda. We want to rearrange for lambda. Lambda equals HC over E. Pop in all our numbers. H is Planck's constant. And that gives us an answer of the wavelength equals 3.4 times 10 to the minus 7 meters. And that gives us 340 nanometers if you wanted to put it into those units there. Question 14. An electron of non-relativistic speed interacts with an atom. Let me just draw that. We've got the atom nucleus, we've got our electrons. This electron comes in and a photon comes out. HF, and that's the energy of the electron. An electron of speed 2v now interacts with the same atom. So it's got a speed 2v, which means its energy is kinetic energy, but it's got speed 2v, so it's 2v squared. So it's got 4 times the energy that it went in with. So this time, when we've got our atom with our energy levels, the energy coming in is 4 times that of what it was before, which means the frequency is 4 times that as it was before. It is D4F. Question 15. In a photoelectric effect experiment, a beam of light is incident on a metallic surface W in a vacuum. The graph shows how the current I varies with the potential difference V when three different beams X, Y and Z are all incident on W at different times. Now we have three statements. X and Y have the same frequency. 2. Y and Z have different intensity. 3. Y and Z have the same frequency. And it says which statements are correct. Let's have a look at this one first. If they have the same frequency, then they have the same energy. And if they have the same energy, then the electrons emitted have the same kinetic energy. But given that the voltage is required to stop this kinetic energy, that means they would have the same stopping voltage. And the stopping voltage is shown along here. They don't have the same stopping voltage. They've got different stopping voltages. So 1 is not true. Y and Z have different intensities. Intensity tells us how many photons are incident. So if they've got the same intensity, the same photons are incident, which means the same electrons are ejected, which means the current is the same when there's no voltage across it. And you can see that the current is different here. So X and Y have different intensities. That's correct. Number 3. Y and Z have the same frequency. Well, let's go back to this argument at the top. If they have the same frequency, they have the same energy, which means the kinetic energy of the emitted electrons is the same, which means the stopping voltage is the same. If we look at the stopping voltage for Y and Z, they do have the same stopping voltage. So Y and Z is correct. Our answer is only 2 and 3 are correct. Our answer is C. Question 16. In a photoelectric experiment, a stopping voltage V required to prevent photoelectrons from flowing across the photoelectric cell is measured for light of two frequencies F1 and F2. The results obtained are shown. The ratio of V2 minus V1 over F2 minus F1 is an estimate of, well, what they've just quoted there is a gradient. So we're looking at the gradient of this graph. So we'll bear in mind that this question is asking us, what is the gradient of this graph? Now, come with me. We have electrons being emitted from here with kinetic energy. And in the photoelectric effect experiment, they've put across a stopping voltage. And that stopping voltage does work on the electron, and that work that it does on the electron is W equals QV, which is EV. If we get the electrons to stop, then the electric potential energy is equal to the kinetic energy of the electron. Now, bear that in mind. Let's do the photoelectric effect equation, and that is HF equals work function plus kinetic energy. And we're going to rearrange that for kinetic energy. EK equals HF minus the work function. So instead of putting EK here, we're going to put this into there. So EV equals HF minus the work function. Let's take a look at that. I'm going to just divide both sides by E. So we've got V equals HF over E minus the work function over E. Now, what I'd like to do is take that and say that's on the y-axis, because it is. Take that and say that's on the x-axis, because it is. This then becomes our y-intercept, which is down here. And that y-intercept is work function over E. And guess what? Our gradient is this, H over E. So the ratio of V2 minus V1 over F2 minus F1 is the gradient of that graph, which is H over E. Your answer is D. Question 17, and this is going to be the last question I do with you, because I feel like we've been through all the really difficult ones, and you can go on to do the last few yourself. In an experiment, a beam of electrons with energy 440 mega electron volts are incident on oxygen-16. The variation with scattering angle of the relative intensity of these scattering electrons is shown. Do you remember the equation I write down when I see this? Sin theta equals lambda over d. Identify a property of electrons demonstrated by this experiment. The property is that they are wave-like. Electrons have wave properties. E.2, show that the energy E of each electron in the beam is about 7 times 10 to the minus 11 joules. We were told that the energy was 440 mega electron volts, which means it's 440 times 10 to the 6 times an electron volt, 7.04 times 10 to the minus 11 joules, which fits up there quite nicely. A3. The de Broglie wavelength for an electron is given by hc over E. Show that the diameter of an oxygen-16 nucleus is about 4 femtometers. We're going to use this equation and we're going to work this out using hc over E. We can find that out with the graph. So I'm going to rearrange it to go D is equal to lambda over sine theta. Lambda is equal to hc over E. I'm going to pop in all the details here. And we get a value for the wavelength of the electron as 2.825 times 10 to the minus 15 meters. We'll leave that at the moment. Then we want to find out sine theta. So sine theta is equal to, let's go up to the graph. Theta is equal to 46 degrees. Sine 46, 0.7193. Let's pop this stuff in. That's going to give us a diameter of 3.93 times 10 to the minus 15 meters. And I think we need to give it to, it says about 4 femtometers. So if we give it to one significant figure, 4 times 10 to the minus 15 meters, which is equal to 4 femtometers. Job done. B. Calculate the volume of a tin 118 nucleus. State your answer to an appropriate number of significant figures. The radius of a tin 118 nucleus is r0 a to the power a third. That's the Fermi nucleus, which is in your data booklet, times power a third. So the radius of that nucleus is 5.886 times 10 to the minus 15 meters. We then know that the volume is spherical, so we pop it into this, get all those details together, and that volume gives us an answer of 8.54 times 10 to the minus 43 meters cubed. And it says, state your answer to the appropriate number of significant figures. The least amount of significant figures given here is 2, so let's give it 2 significant figures, 8.5 times 10 to the minus 43 meters cubed, which is tiny.